Hi there. I want to welcome you to my presentation. My name is Janis Griffin, and my presentation is Need for Speed. These are my top 5 Oracle performance tuning tips. Okay, so just before we get started, a little bit about myself. I'm a longtime DBA, over 30 years of experience. I started out with version Oracle 3, and Oracle and version 3, if you will. I've also worked with many other database types. My strengths are Oracle, of course. What used to be Sybase is now SAP ASE, SQL Server, and MySQL. I've always been a DBA. I've worked mainly on the development side of creating applications and doing logical data modeling. I've specialized and had my own company for 5 years in performance tuning. And I've been at Quest for now going on 2 years. And actually, I work with our customers and prospective customers as a senior sales engineer. And a lot of times I look at their databases and they want to know how to tune a query. And so that's the reason for my top tips. I am an Oracle ACE, not an ACE director. I have to correct that, but I actually had to step down from directorship this year just because of the COVID and not being out and about in the community. Okay, so the agenda we're going to talk about today is the challenges of tuning. And then we're going to jump right into my top 5 tips. We're going to monitor wait time, talk about reviewing the execution plan, gather object information. We're going to find the driving table, and then we're going to engineer out the stupid, if you will. And that's usually where I find my mistakes. So, and then we're also talking, we'll talk about a little bit, if we have time, if you have third-party applications where you can't change the query, there are some things Oracle gives you that you can actually increase its performance. So let's just face it, SQL tuning is hard. The reason why it's hard is a lot of times it's even hard to figure out who should tune. You think the developer or the DBA should, because the DBA knows how to write good code, should know how to write good code. But often he's concerned, or he or she is concerned just with keeping the lights on and has many instances to take care of. You think the developer should because he wrote the application, but a lot of developers are Java programmers and know nothing about SQL. They use third-party code generators to generate some pretty bad SQL. So even finding which SQL to tune is hard, especially when you want to really increase performance and you're working on the wrong thing. Excuse me. I always like to ask people, have you ever tuned something and nobody notices? Well, chances are you may not be tuning the right thing. It requires expertise. You need to know how to read an execution plan. You need to know which data access path is best for your query, which join method is best. And you need to know how to write good SQL because sometimes you have to rewrite it. I also think it's important that you know the purpose of the SQL. Why is a business running it? I know I worked at a manufacturing firm years ago in the finance department, and every month in they'd come and complain and saying the database is slow. And I started looking around, and here an accounting clerk had inherited a job of running these month-end reports. And when I asked her what she was doing with them, and they were horrific reports, they were 8, 12 hours running. And when I asked her what she was doing, she's just filing them in a filing cabinet. And lo and behold, I'd come to look at them, and no one was looking at them. They were a waste of paper, waste of processing. So that was the easiest tuning gig I ever did, was be able just to shut off those reports. Tuning takes time. There's a large number of SQL statements in a database, and there's no cookie cutter approach. And then finally, some consider low priority in some companies. I worked at a network firm where my VP actually grew up to the ranks of operations, and he had the wallet, so he could throw money at anything. And so he tried to throw money and hardware at poor SQL. And the problem is with poorly written SQL, it'll just consume resources, especially when the data grows and the workloads change. So we're going to jump right into my 5 tips. I want you to be aware to consider these as, just tips as, building blocks for your tuning toolbox. This is not going to make you an expert. And, there are classes that are, 4 days to a week long in just tuning. So, but hopefully these will help you. So tip number 1 is monitor wait time. And what I mean by that is Oracle has instrumented itself by providing not only the total time a query spends in the database, but also it looks at each step the SQL request takes as it gets processed to the database, and records up the time of each step and actually the resource it's waited on or using up and at each step. So if you were to watch that and pull that information, and you could rank your queries, and actually you could rank them by the amount of time the user is spending on them. And so you can see which SQLs are affecting your end users. Oracle does this by providing you wait events, and the wait events are great clues on how to tune. If it's waiting on I/O, and what type of I/O that it's doing, it might need an index, and that's a great clue to tell you not only which SQLs you should work on, but also gives you clues on how to tune it. If you want to create your own tool, you can do that. It's not rocket science. All you have to do is, look at these $V views. Now, these are not all the $V views, and neither are each of these views do not have all the columns either. I'm just giving you the weight information I would pull. And so in $V session, and these are real time in memory table, they're not persisted on disk, but they have performance data. So in $V session, I get the SID and serial number, the username, the machine program. I can get the wait event, and any parameters about that wait event. I can get the state to see if it's waited or waiting, and then I can see if it's a blocking session. I can join that in with the $SQL and get the SQL text. I can join that into the $SQL plan and get the actual execution plan, and then I can get the executions, disk reads, buffer gets out of $SQL area. I can go get the object name out of DBA objects, and then if I wanted to get a bind variable, I can actually capture a sampling of what the values for those bind variables are. And this is a great way to see the data types that are being passed, and a great way to find implicit conversions. Like I said, it's not rocket science. You just have to select from this table at some interval. And I created and called my table wait time analysis data. And I basically just created it and then insert and pull this every second. So I insert and I'm selecting all that good information. And I'm actually putting a timestamp on it, and I'm looking at a $V session, and then I go, look for status equal active. I'm not getting any idle events because that's just noise, and I'm also not getting myself because I'm polling every second, so I don't want to be seen. And then basically, whenever you want to look, you've got the timestamp, so you can either look at all the data or you can actually, go between ranges and answer that question: what happened yesterday at 5 o'clock? So as you can see here, I wrote this little query that actually gets the total count time spent, as well as the wait type and time spent in each wait event. And as you can see here in this query that ends in G76, it spent 27 seconds in the database. 25 of it was on a DB file sequential read. So there I know where I want to focus and try to reduce. If you have the tuning and diagnostic packs, you have a $V active session history, which does the same thing for you. Now it costs, it's in enterprise only, and it costs extra dollars. But the thing is, if you do have it, you don't have to create a tool. You can just go to the $V session history. Now $V session history is only there in 10G and higher. The data is sampled every second, and it only holds at least 1 hour of history in memory. And the way that's configured, it's never bigger than 2% of SGA target if you've got that set, or if you have that turned off, then it's 5% of shared pool. After that, it flushes it to WRH active session history. There's an actual view out there called DBA hist active session history. And then you can see it with this query by going to that, and you can see I have this one SQL ID ending in 5TJ, and it spent most of its time on a log file switch completion, but it also had a lock, and it was also on CPU. Finally, our product Foglight does a good job of wait time analysis, and what it does is it shows and focuses on SQL statements spending the most time in the database. And so this is one of our case studies we're going to go through. It actually came in from a customer, and it's from a university, and they were trying to get their billing out. and they asked us to log on and see if we could find what was wrong and give them some suggestions. And you can see it's a top SQL statement. And with Foglight, you have this multi-dimensional view that's a cube that you can turn it many different ways. You can go down via a user, a database, any of that program, module, and you can actually have it sorted by any of those that is weighting the most in the database. And you see this one is spending 100% of time on CPU, and I get my baseline metrics with this too. And as I tune, I like to get my baseline metrics because I like to know how long it's taking now. And then I always like to figure out what is acceptable. You know, if it's taking 2 minutes and I want it a sub-second, I might be able to do that. But if it's running 8 hours and I want it sub-seconds, then I might have to set expectations and tell them it might be a redesign, not such a tuning effort. And then finally, I like to get buffer gets, because buffer gets, if you think about it, every query has to do at least one buffer get. It may not have to do a physical read, but it has to go look in memory. So I always get buffer gets because you can see here, this one's 935,000 buffer gets when it did 1,500 rows and 1,500 executions. So it seems kind of excessive. I also like to get the weight information. Now you might have more than just one weight, event. And like this one, I have log buffer space, but I also have busy buffer weights and log file switch, problems. So I have more than one, but I usually work with the one with the most weight and try to reduce that one. And sometimes the other weights will go away. Sometimes, I'll have multiple resolutions and have to work on those as well. Other benefits of wait time analysis is you can see changes because you're pulling that every second. You can see changes happening. So here I had an execution plan change and a slowdown. It was running under a second and all of a sudden it started running 2 seconds. Well, why? Well, as you can see here, there was an execution plan change. And you can go down and compare that. You can see, well, before it was using table access by index row ID and it changed to table access full. So naturally it slowed down. Okay, so we found our SQL statement and we've got some clues on how to tune. So now what do we do? Well, tip 2 is to review the execution plan. And Oracle gives you many ways to review. You can get that execution plan. You can do an explain plan. The thing about explain plans, they're estimated plans that can be wrong for many reasons. It's Oracle's best guess. It's blind to bind variables or any data types. It just looks at the columns only. You can run explain plan, but with an explain plan 4 and give it the SQL statement, or you can, and then you can display xplan, DBMS xplan display to see it. Or I like to set on auto trace to trace because then I don't have to see all the rows being processed. It just shows me the explain plan. You can also trace and with TK-Prof, but the problem with that, it does give you all sorts of good information, but you got to know when the problem is going to occur because TK-Prof can, affect performance, and it's a lot of data to weed through just to find an execution plan. Finally, $SQL plan, that's what I like to use is the actual execution plan that's cached, and you can use DBMS xplan display cursor to display it. And then there's also historical plans, AWR, and of course Quest Foglight, and they'll show plan changes over time. Okay, so how does an execution plan get created? Well, once a new query gets parsed, sent to a parser, then it sends it to the query transformer to rewrite the query to be more efficient. And it looks for these things over here. It looks for view merging, subquerying and nesting. It does all of those, and it looks to rewrite it. Once it transforms the query, it sends it to an estimator. And the estimator looks at the selectivity, the cardinality, the cost, and it actually goes to the data dictionary and looks at the schema definitions and all the information it has for statistics. And it sends all that and the query to the plan generator. And the plan generator creates multiple plans using different access paths and join types. And then once it comes up with the lowest cost plan, it'll send that default plan to the row source generator to create an execution plan. Now, the execution plan steps basically show the sequence of operations performed to run SQL statements. It shows you order of tables referenced in the statements, access methods for each table in the statements, such as it's accessed by index, it's doing a full table access or a view. These are not a comprehensive list of any of these different methods. I just put some in so you get the idea of what I'm talking about. Join methods, it shows you how it's joining tables, and it'll show you either hash joins, merge joins, nested loops. Those are the three most common, but there's others. And then data manipulation, any concatenations, counts, filtering. It also in 12C and above, it's also instrumented itself. The optimizer is smart enough now to instrument itself with statistics collectors. So it actually samples as it's running some couple buffers of data to see if the statistics are better than the default statistics. Okay, so once we get the execution plan, we have to examine and look for expensive operators. And not that costs matter, it's just I compare all the steps and see which costs are the most costly. And look at the row counts and the time of each step. I also look for any expensive steps like full table scans or index scans. And not that they're always bad, but you want to make sure if you're doing index scans or table scans that they're warranted. Review the predicate information, know how the bind variables are being interpreted, review the data types, look for and be careful of implicit conversions because they are very CPU intensive. And typically databases shouldn't be CPU intensive. Usually if they are, they're doing a lot of logical reads or they're having to do implicit conversions. Know which step the filtering predicate is applied. And I always like to have the filtering predicate applied earlier rather than later. So, you're getting very few rows back and then building upon it as opposed to joining all the data and then throwing it away at the end. Review the join methods. Nested loops are good for, if you have a very large table and a bunch of lookup tables, like master and detail, nested loops are good for that. Hash joins are better for large table joins. So always be kind of aware of that. And then finally now in 12C and above, the notes section is becoming increasingly important because it's showing you what is supporting that plan, what features the optimizer is using to support that plan. Now here's just a real simple query. We're looking at our imp and dep tables, and we're selecting the employee number, employee name, and then department and hire date from employee or imp and dep, where the department number is a bind variable, and then we join on department number. And notice I'm using $SQL, using the dbms xplan display cursor, and I get it out of there. I pass the SQL ID and the child name or child ID. And as you can see, it's accessing department first with the primary key of department, and then it is actually doing a full table scan on employee. I look at the cost, and it's 15, and my costliest step is the full table scan. I also look for implicit conversions, and it is doing an implicit conversion, but it's doing it on my bind variable. It's not doing it on the department number, which if you're doing it on the department number, it could turn off that index and it would do a full table scan on department as well. Like I said, you need to know which optimizer features you're using. And in 12, this is becoming increasingly important. Even in 19 now is even important. But these are the main ones that you want to look at. And you can show parameter optimizer. And then in 12.1, they only had one parameter that actually controlled all the optimizer features. And so it actually turned on adaptive plans, which is adaptive plans are join methods, which can change from nested loops to hash joins or vice versa, or the parallel distribution, for parallel queries, or it could decide to go parallel if it needed to. And then for adaptive statistics, we turned on dynamic statistics, automatic reoptimization, and SQL plan directives, which we'll talk all about. But the main thing is these are default values that come out, so you want to make sure you know what is supporting the optimizer. So in this case, I'm not capturing baselines. That by default is set to false. But if there is a baseline, it's using it. You can also look to see if your invisible indexes are turned on, because if they are, you may not be using an index and can't figure out why, and it has been turned invisible. Different things like that. In 12.2, they actually changed and actually got rid of this feature, the optimizer adaptive features, and it actually gave us two options: optimizer adaptive plans, and then optimizer adaptive statistics. And they actually changed the statistics to false. And the reason why, I think they had a lot of problems, a lot of companies had problems with that happening behind the scenes. It was creating too many directives. Okay, so like I said, there's a lot of things supporting an optimizer. There's baselines, profiles, outlines, and packages. There's dynamic statistics, statistics feedback, or SQL directives. There's adaptive cursor sharing. There's adaptive plans. Notice your notes section is getting more important. So here you can see on this one, statistics feedback was used, and it also adapted from nested loops to hash joins or vice versa. Here's an example of baselines. And, if you don't know if you're using baselines, you can select star from DBA SQL plan baselines. And, then when you go get it, you can actually see it in the note column that is being supported by this one baseline. Here's an example of adaptive plan. And when you want to see what happened in the adaptive plan, whether it was nested loops that it changed to, or whether it was hash joins, you have to use this format parameter. So I'm doing display cursor, SQL ID and child number, but I put format equals plus adaptive, and then it'll tell you the rows with the hyphen are inactive. So it actually was thinking about doing hash joins, and then after it sampled with its statistic collector, it decided to do nested loops. Instead of a full table scan, it actually used an index. So kind of a neat feature to actually be able to see that on the fly. There also is a parameter if you want to turn off adaptive plans, you can turn them off, and what happens, you can actually turn on this reporting only parameter, and so it'll adapt the plan. It won't adapt the plan for real, but it will show you what it would adapt to by using this plus report. Okay, so we found our SQL by monitoring wait time, and we looked and got a good idea of our expensive objects in the execution plan where we want to focus. Now my tip number 3 is gather object information. And when you do this, what you really want to do is you want to understand the objects, expensive objects in the execution plans. You want to get the table definitions, the segment sizes, and you got to figure out is it really a table? It might be a view, and then you have to kind of look at the underlying definition. Know the number of rows, know if there's partitioning involved. Examine the columns in the where clause. Know the cardinality of the columns. Know if there's data skew within those columns, and if there is what histograms are supporting it. Also gather statistics. Look at your statistics, see if they're out of date, because that can impact performance. There's a neat tuning script in the appendix of these slides if you download my presentation that you can just run. So I did that for my imp and depth tables. And you can see for employee, I've got the columns names here, but I don't have any indexes. And then you can see the column distributions. You can see I do have 4 frequency histograms. I can actually even get the histograms, further information on the histograms, and I can see the data skew. I can also see, when it was last analyzed, and my imp table is 18 meg. Also review the indexes and constraints. Get the index definitions. Know the order of the columns if you've got a composite or a multi-column index. And it's also important to consider the selectivity of those columns. You want the most selective in the left leading column, or left leading in the index. Review the keys and constraints. I think if you have a lot of tables in your query, it's always easy if you've got SQL Developer to do a data model and actually see the relationships. And you can quickly see the check constraints and not null constraints as well. But what you want to look here for is, the relationship. So when you're in your joins, you're giving it all the information so the optimizer can get the best plan. So here's our little university query, and we've got registration with a primary key on student ID, class ID, and sign up date. With a foreign key from student, and student has a primary key on student ID, and a foreign key to class, and class ID is a primary key in class. And then finally, make sure the optimizer can use your index. Functions on indexes can turn off an index, so you might have to consider using a function index, which is you can do in Oracle. Also look for implicit conversions. Get sample bind variable values. And this is what I did to get it. You can go to $v bind capture and get a sampling of what's being passed to those bind variables. And that way it'll tell you if implicit conversions are happening. Also, make sure the index is invisible, because if it's invisible, Oracle may not use it. Okay. Understand your statistics gathering. This is important, and Tom Kyte, and this has been a while because DBMS stats was rewritten in 11G. And so you should only be using 2 to 4 parameters per Tom Kyte. Now that is the schema name, table name, partition name, and degree of parallelism. And so, because in 11G, they rewrote it, and auto sample size is 100%, does 100% of the table in less time and is more accurate than a 10% estimate. So avoid using estimate percent. If you want to see the defaults, you can do the new get prefs function, and I'll show an example of how to do that down here. And you can see that I've got auto sample turned on here, and not using any type of estimate percent. The optimizer now tries to fix statistics mistakes, and it does this in several different ways. One is dynamic statistics, and if you have missing, insufficient, or stale statistics, there's a new level in 12C. This is not a new thing, but now you can set it to level 11, the optimizer dynamic sampling. And what this will do is tell the optimizer it can automatically sample when it needs to. Statistics feedback is another way, and this is where it implements those statistics collectors on the first execution, and then it compares the default stats with the actual rows sampled, and if they're significantly different, it actually stores the correct estimates in the $v SQL reoptimization hints table, and it uses opt estimate hints in that, so you can see all that in $v SQL reoptimization hints. SQL plan directions are another way that it can change column group statistics or histogram. And what it does is it actually dynamically samples the data on the directive. And for example, a column group could be city, state, and zip. And so it looks at that column group and it'll create a column group statistics. It's not tied to any SQL statement, so it's defined on a query expression. So at any time you've got city, state, and zip in a where clause, it'll use that SQL plan directive. Find the driving table. Now this is my fourth tip, and basically what I mean by that is you're going to want to drive the table. You want to drive the query by the table with the smallest amount of data that's returned, as opposed to bring back data on all of the tables and then joining them and then throwing the data out. So you want to find data with the least amount of data and build on it. So you can kind of look at each step and in the joins, figure out if you're doing right, left, or outer, and then look at the filtering predicates, and then try to filter earlier rather than later. Now you want to compare the final result set with the amount of data read to with buffer gets. So you want to try to reduce those buffer gets. So here's our little case study. We're selecting, this is this university study, and we're selecting first name, last name, sign up date from student. And we're joining student on registration on student ID, and we're joining class on class ID. And then basically our filtering predicates, we're looking for name equals SQL tuning, and for sign up date between yesterday, if you will, and they had a registration and a canceled flag. They never deleted from it. So if a student dropped or canceled, they just mark it to Y. So we were getting current records only. And this was, like I said, this came in from a customer, and they were simply trying to get their billing out, and it was so slow. And they called us, and we jumped on to see what was going on. I've changed it somewhat, to kind of go with this class. They were looking for all classes. I'm looking for SQL tuning. But as you can see, the first thing I did is I went and looked to see that it was a top query, and it was. And you can see, spent a lot of time in the database, and it was not that inefficient on my instance. But look at the amount of buffer hits. It did about 5. Let's see how many executions. It did quite a few executions, but it did 118 million buffer hits. And a lot of the top weight was cursor pin S weight on X. And so now I've got my baseline metrics. 0.01 seconds to execute. It was spending 57% of its time on CPU, and then it was the weight was on cursor pin S weight on X. So we go get the execution plan. You can see right away what it did. It basically did a hash join on class and registration and full table scans there. And then it did an index unique on student. Now notice my cost is 114. The biggest step here is registration of 105. I do have an implicit conversion here, but on just my bind variable. So that looks probably okay. But this is an adaptive join. And so it's doing hash join. And this doesn't look right to me because, it's doing a hash join on two lookup table, on a lookup table and a full big table. And typically you want that to use nested loops. Okay, so let's go get the information on the objects. And you can see the data model there. You see registration is 80,000, student is 10,000, class is 1,000. And you can see the different indexes here. We've got, one on registration, which is student, class ID, and sign up date. We've got, there's the distribution of it. And we've got some histograms. Then you can see the size of all that. So what does a tuning advisor recommend? And I thought it'd be kind of fun to go try the tuning advisor and see what advice it gave. So basically I declared a task and I created a task and then I reported on the task. And basically it came up and said it wanted me to add two indexes. So as you can see here, it says, consider this, adding one on class with class name and class ID. And the other one was added on registration, canceled, sign up date, class ID, and student. Should I do it? Well, that's one thing I like about SQL diagramming. It gives you the best execution, the best driving table without having tools do it for you. So it helps you rationalize if you should do it or not. So there's a great book out there, SQL Tuning. It's by Dan Tal. It's an oldie but goodie that teaches SQL diagramming if you don't know this technique. I've never met the man, but I do like the book. It actually has Oracle, SQL Server, and Sybase. I think he goes through case studies of all those. But basically what you do is you draw an upside down table, tree, and you put your detailed table up top and your lookup tables, you draw these links or arrows out to the lookup tables. And so we had three tables. Registration was our detailed table, and it had two lookups, student and class. Now, the numbers on side of the arrows here are basically the average join records they have to read for any one student. So for any one student, I have about 5 records of registration. And for any one class, I have about 30 records in registration. Now, in a university, that's probably not true, but in my data set, that's how that worked out. The numbers with the line underlined that are underlined here are actually the filtering predicates. And you can see here I had 2. I had one on registration where canceled equals in and sign up equals yesterday, if you will. And you can see that 5% of registration would be read with that filter. I had another filter on class where 2 records out of 1,000 were returned, and that's probably because of the different, levels of SQL tuning. 0.2% would be read of class. So my better filter and my driving table should be class. So I want to drive that table by class. So I can come down here and I created an index on class name. And already, you can see it's using it. And look at my buffer gets way down. They are now, instead of 118 million, they're 3 million. Problem is, my average response actually went up. In my executions, my throughput kind of went down. So let's figure out why. And it's still doing a full table scan on registration. Well, because registration, it can't use class ID because it's not left leading student. So because I don't reference student ID in the where clause, it can't use this index. So let's go create an index on registration. And when we do that on class ID, you can see we went back and we went to 61 million on buffer gets, back down our average response time, but it's still less than 118 million from the beginning. So it's a better plan. And we are using both indexes now. Now let's take all that off and let's create what the tuning advisor suggested. And so we created an index called reg canceled sign up on registration cancel ID sign up date class ID student. And we got it down to 4 million again. And throughput executions were quite, but look at our cost. Our cost got down to 23. So as opposed to the original one, I think it was 114. But I didn't like the way that that index was created. Canceled was not selective. The most selective was class, followed by sign up date, I believe. And student was already indexed, so why did I need to put that in there? So, and I didn't think it warranted a covering index. So basically, I did class ID, sign up date, and canceled. And the reason why I did that order is because of the most selective to the least selective. And you can see I reduced it to cost of 11. The buffer gets are still down at 4 million. And so I did improve it. So sometimes the tuning, advisor gets us close, but not always there. Did we improve it? And this is another feature of wait time analysis. You can see if you've improved it over time because I could go back and look. And so when it was running without any of those indexes, this is the gray line. And when I was, finished tuning it, you can see it even stopped running at times. That's why that's kind of shaded, but it was so efficient. And look at my, look at the, throughput. I had 5 sessions running this just over and over again. So because it increased in performance, it was so efficient, and it actually increased throughput. Okay, tip number 5, and this is, like I said, one that I find myself in a lot, is look for engineer out the stupid. And you want to look for anything that's affecting performance. Cursor or row by row processing. Sometimes when you're in a hurry and you just want to get the answer, I think logically, so I want to do row by row processing. But databases like set processing. Parallel processing, you don't want to use it in an OLTP environment. You only want to use it in large data sets. So if you're going and using parallel processing, you're actually, stealing processing power from other things. Look out for nested views that use database links, abuse of wildcards or nowhere clauses. Like I said, third-party generators, SQL generators can, cause very bad SQL and try to put all the data over on the client. And, databases are great filtering machines. So why do that? Use functions on index columns. Using them actually slow things down. The optimizer can't use an index. Instead, move the function to the constant. I seen this one the other day where, it came in from a customer and they were selecting last name and they were uppering, and actually passing in a literal. I suggested they do it this way, select and actually put a bind variable in it and then upper on that side. They could have added a function index too if they couldn't change the code, but that's just sloppy coding. And also beware of hard-coded hints. They can, as a SQL, workload change and data changes, they can be obsolete and forgotten about. Here's just some more do's and don'ts. Reduce sort operations. Try to use union all instead of union, and also don't use distinct. I see this quite common, that developers always want to use distinct when they don't necessarily need to, and that'll cause a sort. When using composite or multi-column indexes, access the left leading column in the where clause. Otherwise, if you don't, Oracle tries to fix it with an index skip scan, and that's no better than a full table scan. So try to avoid that. Try to avoid Cartesian product queries. Try to use bind variables instead of literals to reduce the parsing. Also use subqueries. If you use subqueries, try to make use of exist operator. The optimizer will stop with a match and avoid a full table scan if you do that. And then try to use an index if it's less than 5% of the data needed to be accessed. The only exception to that is if you have a very small table, you may want to keep it in memory and do a full table scan, because that might be more efficient. Also, look out for equijoins whenever possible. Try not to use not and not equal, or not null, because the optimizer has more choices to choose from, and it gets confused. Also, avoid complex expressions as NVL, to-date, to-number. They prevent the optimizer from assigning valid cardinalities or selectivity estimates, and it can affect the overall plan and the join methods. Avoid joining complex views, because it has to instantiate all the tables, and you may not need all the data from all those tables. So go to the table directly. And they use the partitioning key if you have partition tables in the where clause, because partition pruning will be used to reduce the amount of data read, and it'll stop a lot of memory thrashing and high CPU. When you need to use hints, if you can hint it, and this again came from Tom Kyte, baseline it. And alternative, it's a great alternative to using hints, because you can change it behind the scenes on the fly. Hints are difficult to manage over time, and you usually forget them. But you can use this if you have third-party software that you think you need an index, but you can't modify it, or you think you can rewrite the query some way. You can do this technique and actually change the execution plan. So here I have a query, and I'm actually selecting product from order items and product. And I'm looking for unit price equals a bind variable, order quantity is greater a bind variable, and product ID equals product ID. And then that product ID has a bind variable. And you can see what it was doing. It was doing a merge join Cartesian. And I don't want that. You want to try to avoid Cartesian joins. So what I did is I put in cache, use nested loops on product. And so I gave it that hint. So now it's doing nested loops, which I want. And so then what I did is I went and got them out of cache. I got that my query out of cache. And I actually said, load this query into cache, into a baseline. So I said, load plans from cursor cache, and made a baseline out of it. When I did that, I went to the table of DBA SQL plan baselines, and I actually altered the original one to be enabled no, and then I enabled my nested loop one. So it actually, I didn't change the code, I didn't do anything, but actually change the baseline. And it's an easy fix if you have to change third-party software. If you have problems with stabilizing plans, a good thing to use, and always remember, is baselines. You can use profiles, I don't, or patches. And so it's a good way to do it. So you may want to look into all of those techniques. Here's just another case study to run through the 5 tips again. And so this is on HammerDB I use a lot, and this is one of their queries that I modified somewhat. And what's nice about this is I can put a load. I usually got 5 users on it. And so this is actually getting orders by customer last name. And you can see it's joining order line, orders, district, customer, and stock. It has a bunch of filtering, and it's join criteria. And we're doing customer last name like, and passing in a bind variable. And you can see it's my top query again running in this database. And I've got my metrics. We found it by wait time analysis, and it's doing 24 million buffer gets. It only did 671 executions. So we go get the execution plan, and you can see here that it has got quite a few problems. It's adapted. It was going to do nested loops, but it looks like it changed to hash joins. Here it's doing a table full on stock. It's doing an index skip scan, which I don't want on order ID 1 or order index 1. And then it's doing a table access full on customer. So the cost is quite high at $6,099. And my costliest step there is stock. So let's go look at the objects. And what we can see right away is stock has no index. So that's one thing we want to fix. So let's add an index on stock. We're doing it on item ID, warehouse, and quantity. And we can also get more information. We've got a few histograms, and we can see that there, as well as we can see the size and when it was last analyzed. Let's go get the object information. We can see we have an index on orders. I mean, orders engine, orders table, and we can see that we have one index on there. That's at orders I1, and basically we do have some histograms, and we see the row counts there, and we got about 60,000 in orders. So let's try to find the driving table. And this is why I chose this query, because it has more, more relationships. And so we've got order line was our detail table. It'll look up into orders, and it'll look up into customers. And I'll look up into stock, and I'll look up into district. District had a look up into warehouse. So you can kind of see that. Now, the numbers on the arrows, of course, is a join criteria. I don't often do that in reality, because as long as you make sure the columns that are in the joins are indexed, the optimizer will do the right thing. So I actually avoid doing these numbers on the arrows. I think it's more interesting to go to the filtering criteria. So on this, I had 3 filters. I had one on order line, and that was going to be 0.7% of order line was going to be red. And then I had one on customer, and that was 0.03% of customer would be red. And then I had one on stock, which is 1% would be red there. So my best driving table would be customer. So first, let's go see about what we did when we added that index on stock. I got rid of my costly step, and you can see 215, it reduced down the cost, but I still have that index skip scan, and the customer is still doing a full table scan. This adapted again, but you can see my buffer gets were now down to 6,000 as opposed to what the previous cost was as well. So I mean, 6 million is the buffer gets, and the previous cost was 6,099. I decided to try to get rid of that skip scan, and so I created index on orders. And I did it on order ID, customer ID, and order entry date. And I'm doing 11 million buffer gets, and my cost actually went up a little bit. And I actually, so did my buffer gets. So probably not the right thing. I didn't do much improvement on this. What I really should have looked at is try to drive it with the customer table, because that was my best filter. So in summary, there are a lot of challenges with tuning, but if you remember my top 5 tips, they'll take you a long way. Monitor wait time, look for wait events, record baseline metrics, review the execution plan, look for the expensive steps, know what the optimizer features are, what optimizer features are supporting that plan, and then gather object information for expensive objects, know what the optimizer knows, and then find the driving table. You might want to consider using SQL diagramming techniques. And then again, always look for the stupid things that you might put in there because you're in a hurry. And if you can't change the code, or you have plan changes, you need to stabilize them, consider either using baselines, patches, or profiles. And that's it. I will be online and answering questions if you have any questions, and I want to thank you for joining me today. Thank you.